Welcome to the presentation on the problem first completely painted row or column. In this problem, our goal is to find the first step where a row or column in a matrix is completely painted. Let's start by understanding the problem statement. We are given an array of painting steps where each step corresponds to painting a particular cell in a matrix. Our task is to determine the first step when either a row or a column in the matrix is completely painted. We are provided with two inputs, an array ARR which represents the painting steps and a matrix mat which is an M cross N grid. Our output should be the index of the step at which the row or column is fully painted. To solve this problem, we follow these key steps. First, we will use a hash map to keep track of the position of each matrix cell. We will maintain counters for the painted cells in each row and each column. Then we will iterate through the painting steps and update these counters. Finally, we will return the index of the step when a row or column is fully painted. Here's an overview of how our code will be structured. First, we parse the input. Next, we map the matrix values to their respective row and column indices using a hash map. We use arrays to keep track of the count of painted cells in each row and column. We then iterate over the painting steps and update the counts. If we find a completely painted row or column, we return the current step index. Let's dive into the first step. We need to map each matrix value to its corresponding row and column position. For this, we use an unordered map. In this code, we loop through all the elements of the matrix and store each value with its row and column index. This results us to quickly access the row and column of any cell during the painting process. Next, we initialize two arrays, row painted and col painted, to track the number of painted cells in each row and column. Initially, all values in these arrays are set to 0, indicating that no cells are painted yet. Now we iterate through the painting steps. For each step, we find the position of the corresponding cell using the hash map. Then we increment the painted counts for the row and column of the painted cell. After updating the counts, we check if any row or column is fully painted. If so, we return the index of that step. Lastly, we include an edge case handling mechanism. If no row or column is fully painted after all the steps, we return -1. This should ideally never happen, but it's a good practice to handle all edge cases to make sure our solution is robust. Here is the complete code that implements the solution. We start by mapping the metric values to their rows and column indices. Then we initialize arrays to track the number of painted cells in each row and column. We loop through the painting steps, updating the counts and checking for a fully painted row or column. Finally, if a complete row or column is found, we return the step index. Let's analyze the time and space complexity of this solution. The time complexity is big O of m plus m times n for mapping the values in the matrix to their positions, plus big O of k, where k is the number of painting steps in the array. So the overall time complexity is big O of m times n plus k. As for space complexity, we use a hash map and two arrays for tracking painted counts, which gives us a space complexity of big O of m plus m times n. In summary, this approach efficiently uses a hash map for constant time lookups of metric cell positions. By tracking painted cells in each row and column, we simplify the process of detecting when a row or column is fully painted. The code structure is modular and easy to maintain. Let's go through an example to understand the solution better. Given the array ARR with elements 1, 3, 4, 2 and the matrix mat with elements 1, 4 and 2, 3. If we first map the values to their positions 1, 0, 0, 4, 0, 1, 3, 2, 1, 0 and 3, 1, 1. Then we process each step. In step 0, we paint cell 1 at position 0, 0. Then we paint cell 3 at position 1, 1, followed by painting cell 4 at position 0, 1. Row 0 is now completely painted. The output is step 2. That concludes the explanation of the solution. If you have any questions or would like to discuss alternate approaches, feel free to ask. For instance, what optimizations can we apply if we need to handle large matrices or more complex cases?